All right, we're doing applications of quadratic functions, and this is part one. Basically, one might say, well, these quadratic functions are very nice, but what good are they? And that's what we're here to determine. So we're going to show you what good they actually are by solving a variety of problems. Now, before you start, I want to show one really important feature of all quadratic graphs, and that is if they open up like this. Okay, so let's say you get a graph like this. This is the lowest point right here. So this is an important point called the minimum. Okay, so minimum. And if the graph, say you graphed a different function and it opens this way, opens down, then you have a kind of a highest point, and it's called the maximum. Okay, now this is an important observation because sometimes we are looking for minimum values or maximum values depending on the context of a problem. Notice that the minimum and the maximums occur exactly where the vertexes are. And so it's all about finding the vertex, and that's going to be our strategy when I answer some of these problems that are coming up. So let's start off with one here. We're going to clear the screen, and let's say you are going to build a pen, and you have 1,200 meters of fencing. Okay, so you have 1,200 meters of fencing. And you're going to build this enclosure. So you want to build some kind of an enclosure, and you're going to do it up against the river. So I'm going to draw a picture of it. So here's the river, say, something like this. Okay, we'll give it some waves. So there's the river, and what you want to do is you want to come along here and take your fencing, run down this way a little bit, run across like this, and then run your fencing back up. Now, I didn't draw this very well, but it's supposed to be a rectangular shape. Presumably the river runs perfectly straight, not quite like in my drawing. So this is supposed to be a rectangular shape, and we would like to maximize the area. So the goal here, if you were the farmer or whoever, you want to maximize the area of your enclosure. And you want to know exactly, with 1,200 meters of fencing, how big should I make these sides, the three sides, so I've got maximum area. So I'm going to start with labeling the sides. These are the things we would ultimately like to solve. So I'm going to call this W for the width, and of course it's supposed to be exactly the same length over here. And then across the one long side here, I'll call that the length. So those are my variables, W and L. And so the area of this thing that we want to maximize is W times L. Okay? So what I've done here is I used a sketch to kind of show what the problem is, but you notice I went over here and I created the function, an area function, that we wish to maximize. Okay, so we want to maximize the area. Now the problem right now is you got one too many variables on the right side here. So we have to figure out some way to swap out one of these variables so that we only have one variable on the right side. And here's what we're going to do. We're going to take this business of 1,200 meters of fencing. We're going to say, well, if I look at my drawing here, my fencing would be 2 W's plus an L, and I got to use all my fencing, so that's going to be 1,200. Well, it's pretty easy for me to isolate L. All I'm going to do is subtract the 2W to the other side. Okay, so subtract 2W. And now I'm going to take this expression, which is equal to L, and I'm going to put it in over here where that L is. So here's what my area function looks like. We have W times, instead of L, I'm going to swap it out and put in 1,200 minus 2 W's. Okay, and what I like about this function now is it's an area function that has only one variable on the right side. And if you think about our quadratic functions, this would be kind of along the lines of saying we now have an f of x function. Now, I'm just showing you that it's the same kind of idea. And let's say instead of w, I used x. But you see how we have f of x is the name of our function, and over here we have only the one variable, only the x on the right side. Now, of course, we use w, but I'm just making the point. This is what you want. You want to build a function with one variable on the right side. So why don't we go ahead and have a little look at that. I'm going to clear the screen here. And let's take a little look at that function a little closer here. So that function, our area function, okay, we'll go back to a's here and w's, looks like this. We had w times 1200 minus 2w's. So what I want to do is I want to find out what the maximum of area is. And that means I really want to identify where is the vertex, because that's where maximums or minimums occur. In this case, it's going to be a maximum. But I want to find the vertex, and that's the real work. So what would I do if this was any other quadratic function? Well, I'd expand out the brackets. Okay, so let's do that. So w times 1200 and w times the 2w's, so that's negative 2w squared. And let's just rearrange the order so it's a little bit easier to read. Negative 2w squared and then plus 1200 w's. Now, I get a choice. I can go straight to the vertex formula if I wanted, or I could just go ahead and complete the square. It doesn't matter which process you'd want to use. If I was going to use the vertex formula, well, all I've got to do is identify A, B, and C. Interesting, C is 0. It makes it a little bit easier for us. So where is that vertex? Well, let's have a little look. In the formula, it's going to be negative B, negative 1200, all over 2 times A. So that's 2 times negative 2. And then I could carry on. C is 0, so I won't even write it. And then I have minus B squared, so pretty big number, so 1200 squared, all over 4 times A, so 4 times negative 2. Well, this is the point where the maximum is going to occur. Let's just see where that point is. Negative 1200 divided by negative 4 is 300, so 300. And I could certainly work this out, but I got to ask myself, do I really need to know what this number here is? I mean, if you want to, you take your calculator and you go, well, it's negative 1200 squared divided by negative 8. And I think you're going to get something in the neighborhood of 180,000. But you actually don't need that number, because what we really care about is where is that vertex? I'll just clear a little bit of space here and I'll show you what I'm talking. Actually, you know what, I'm going to just put well, maybe not the grid. But let's clear some space and I'll show you what I'm talking about. Okay, if we were to graph this, okay, we'll just do a very simple little graph here. We know that the vertex was at 300. Okay, so we would have gone 300 to the right. So let's say that's 300. And then we know we had a vertex here. It was 180,000. So we would go all the way up to 180,000. Let's just say that's here. 180,000. So that's where my vertex is. And if I went ahead and I figured out, say, a y-intercept or something like that, I would recognize that the graph is going to open down. Okay? I don't really need to know that this is the maximum. What I really need to know is that that's when it occurs. Remember, our function looked like this, A, and then I had a bunch of stuff with w's. So this, instead of x, this is the w axis, And instead of a y-axis here, this is actually the a-axis. What it's telling us is that the vertex occurs when W is 300. And that's my maximum. So if you think of our little rectangle, we want the width to be 300 if we want to maximize the area, which means the length has to be 1200 minus 2 times W, so 2 times 300. So that length is 600. So if you build your rectangle 300 by 600, then you're going to maximize your area. And that's where I'm going to stop with this first question.